yesterday we discussed about OLS. Okay, I will write here. Ordinary. I will write for. So we have ordinary. Least square. Okay, if you are unable to see, let me know. Okay. Ordinary scale, that is known as OLS, because we are dealing with it now, and the next chapter, this whole chapter, third chapter, is completely based on this. And it is not, I told you, it is not small chapter. There are so many practical derivations to prove few things and to do the practical example. So this chapter is completely based on the ordinary least square. Okay, so what I was saying, so yesterday I defined it like what is OLS, ordinary least square. And I didn't go through it completely, but I was giving you the background. Why do we choose a particular model? Whether it is OLS, whether it is any other model, it is not only about OLS. In our syllabus, it is OLS now. Whether it is any other model, the selection of model depends. The selection of model completely depends upon the selection of model completely depends upon the characteristics of the data. Okay, depends upon characteristics. Characteristics of the data. Okay? I am writing it online, no? So it is like random. It goes like there. So just adjust. I will write big words. No problem. So any model you select, whether it is OLS, whether it is JLS, whether it is ARDL, whether it is a VAR model, VAR, vector error correction model. No, vector, that is VEC. VEC is vector error correction model. VAR is vector autoregressive model. Okay, and then these are all parts of these models. Okay, and ARDL, autoregressive distribution like model, that is based on the OLS, and co-integration model, and error correction model. So many models are there, and one more model, logic model, probit model, logistic regression. Okay, there is one is, we are doing two types of regression. One is this simple regression. One other regression is here. Unfortunately, I forgot the name of that regression, type of regression. Pooled regression or something is there. So that is also, that regression is also there. So that depends upon the data, the availability of the type of data we have, and the properties of the data. Characteristics, I told yesterday. Characteristics means properties. Don't confuse it with anything. When I say characteristics means, it is properties. It is not the character of human character. It is characteristics, properties of the data. That completely depends upon any selection of the model depends upon the characteristics or properties of the data, whatever the data we have available. Sometimes we use large, sometimes we use log models also. Those log models also depend upon the necessity or the requirement of the data. Fine, let us stop it here. Now let us go ahead with the OLS. For example, in our case, for example, in the economics or econometrics, one and the same thing. In the economics, we have two concepts. One is, as I have told you, one is the major thing is sample regression function and population regression function. We have population regression function and sample regression function. Now I will try to make you understand what is the importance of ordinary least square. Till now we have learned about many things, these things, like what is data. In the last class I told you what is data, types of data, different types of data, qualitative data, quantitative data, that I have defined already in the last class, which I have shared the PPT with you also, and scales of data, ordinal, nominal, ordinal, interval, and ratio, that also I have defined to you. No problem in that. Now I will only try to focus on what is OLS, what is OLS, and why do we why do we need it? Why it is considered one of the best model or estimation? Why it is considered one of the best model? So before going that, I would like to give you this OLS. This OLS, this method of least square, it is given by Karl Friedrich. Okay, Friedrich Gauss. He was a German mathematician. He was a German mathematician. Okay, so this is associated. This ordinary least square is given by this Karl Friedrich Gauss. So Gauss theorem also, it is called Gauss theorem, and Gauss theorem of assumptions of Gauss theorem. So that is one and the same thing. Or assumptions of ordinary least square method. Next class we will deal with the assumptions. So, and one more thing, I am referring for your reference. I am saying I am referring sometimes two books are, one is Gujarati by examples and one is basic econometrics by Gujarati. Those are the simplest books for you. There are other foreign books also, but you may it may be difficult for you to understand from those books. Okay, so this is if you have this Damodar Gujarati book, basic econometrics. Okay, that is fine for you. Not fine actually. That is one of the best book for you. Can refer that. So this is the mathematician who has given this concept, ordinary least square. So what's the importance of it? For example, we will write one function. We will write one function. That function is yi equals to beta 1 plus beta 2 xi plus u ui. This function is what? This function is population regression function. It's a regression function. It's an econometrics function. Okay, with the inclusion of u. Yesterday, last time I told you, with the inclusion of u, it becomes econometrics function. If it is only beta 1 and beta 2, then it is not econometric. It's a mathematical function. That's one of the important difference. Okay, so it is population regression function. Correct. Then what is the next? For example, as we have discussed in the last class, and as I have told you that always it is not possible, not possible to, what is not possible? To derive the population regression function. It is not always possible because we will not be having that much data, or that thing I have already discussed with you. Why we cannot have always the population regression function? No need to discuss that again. Yesterday, the whole class was on that one. So when it is not possible for us to estimate the population regression function, then what is the next option for us? The next option for us is sample regression function. Okay, I will write that down. Fine. Okay, sample regression function. So sample regression function is equal to yi equals to beta 1. I will not write anything else now, plus beta 2 xi plus ui. It is same. It is one and the same thing, right? No difference. The difference lies here. When we cap it, these are called estimated. Okay, so this is called sample regression function. Fine. So what is the property now? So when this is called sample regression function. Why? Because when we include why like if you say why how like why it is called sample regression function, and what are beta cap. These are called, this called beta cap, beta 1 cap, beta 2 cap, and u cap. So these are called estimated. Beta 1 cap or beta 2 cap and u cap. These are called estimated. Estimated parameters. Okay. Remember, there are only two parameters in it. Okay, don't include third one. These are parameters, and this is error term. So these are, I will write here an error term. So these are called estimated. Beta 1 cap, beta 2 cap, and u cap. So that's why it is how it is differentiated from the population regression function, by putting the cap on it. That time it will become it will be treated as estimated. So that estimated itself means sample regression function. When you see beta 1 cap, beta 2 cap, or u cap, just remember or just diagnose it clearly that it is the sample regression function. It is the estimated one, not the actual one. Okay, so this one is called estimated. Then what is this one called? Beta 1, beta 2. Okay, this is going very bad. Erase it now because it has already saved. I will make it beta 1, beta 2, and u. These are called actual parameters. Okay, and error term, actual, and error term is actual. Okay, no problem. Correct, till now it's clear. Then what is the thing? What is the thing to understand? This is the difference. Estimated, when you calculate the estimated, when you are dealing with a sample. When you are not having sample, when you are having actual data, then there is no need to do the sampling. There is no need to use the sampling method. You directly use actual parameters and the population regression function that will give you the results as it is. Correct? No problem. If you have any doubt, you can ask. Then this, I will go one step further. Then this u, then this y, yi can be written as yi plus ui, but yi cap actually. This sample, this is again same. It is this one. It is this one. Okay. So, right. This again can be written like this. Why? Because yi cap is equal to beta 1 cap plus x. That's why it is written like this. And what beta, what is this called? I will go to the next. Okay, I am not erasing anything. I am just going to the next slide. Okay, everything is saved. Don't worry. I will give the PPT, written PPT. Then what is this yi called? Yi cap. What is this called? This is called estimated. As I told you here, these are estimated parameters and error terms. These here I am indicating. I am not. You are not seeing me. I'm indicating here. These are called estimated parameters and error term. These are called actual. Then what is this y cap called? Y cap will be called. It will be called the same terminology for it. It will be either called estimated or, I'll write it here. Conditional mean. Conditional mean of yi. Got it? No problem, no clear. So, okay, this is all about OLS. Okay, I am not now. I am not. Yesterday's class was very general class. Why do we need everything? Today's class is very specific about OLS only. Okay, so this is called estimated. When the way I told you, beta 1 cap, beta 2 cap. Okay, these beta 1, for example, beta 1 cap is called the estimated beta cap of beta, actual beta. Similarly, beta 2 cap is the estimated beta 2 cap. This is the estimated beta of, of this beta 2. Third one, similarly, y UI cap is the estimated one of UI. These are the these are the properties, not properties. These are the like interpretation of these terms. These are the estimated ones. So beta cap will be the beta will cap will be the estimated version of beta 1. Beta 2 cap will be the estimated version of beta 2, and by similarly U cap will be the um, estimated parameter or estimated error term of the actual error term. And similarly, the first one, UI, YI, this YI will be the estimated actual or estimated function of the actual function. YI will be the estimated function or conditional. It's called conditional mean. Conditional mean value, conditional mean, or whatever you want to say. No problem in that. Correct? Then what is the next? I will move it aside a little here. Then what is the next? Then we have seen, for example, we have seen in the last in this last this here we have seen y cap y equals to y cap plus ui. Then we will write it again here. For example, here I will write it again, or here anywhere. Okay, y cap. No, y cap. Y equals to yi equals to y y cap plus u cap I. Okay? That we have learned in the last slide here. Y cap actual is estimated one plus error. Correctly? Then what is this error equal to? Then this error term will be equal to, if we deal with the error term only, error term will be equal to yi actual one. It is not so clear. I will write it very bold. Yi minus yi cap. Correct? No doubt in it. Why? Because what we want to interpret from it, we want to interpret that the estimated error we have got is equal to the actual line and the estimated line. The difference between the actual line and the estimated line. That error component is equal to this. This is the actual function. This one is actual function. And this one is estimated. For example, correct? So what is the difference between actual and estimated? So we are subtracting actual, we are subtracting estimated one from the actual one. That way we will be able to get the error. How much error we have? How much error we have? And here is the job. Here is the job for us. Okay. First, I will. Oh, that slide has come. I thought I will finish it. I need to include more slides. This is the numerical example for you. Okay. Then here you understood. Then let us go further. Then, for example, we learned that ui cap equals to yi minus yi cap. Then in the last slide, we learned that yi cap minus this is equal to the beta 1 cap minus beta 2 cap xi. Why? Because yi cap equals to beta 1 cap plus beta 2 cap xi. This equal to this. So when we say it minus, this minus will be multiplied or added to both beta 1 and beta 2. It will become minus. Okay, so what is our job? What is the point to highlight here? The point to highlight here is the actual error is equal to the error we are getting is equal to the actual regression function minus the estimated regression function, the sample regression function. Okay, so if I write in the correct error is equal to actual or population, I will write the correct terminology actually. Error is equal to population regression function minus sample regression function. Error is equal to that. So the difference will give us how much error we have. Now, what is our job? Tell me, what is our job? Our job is to, what is our job? Our job is to minimize this error. Our goal is to minimize this error. If we minimize the error, then what we'll get? We'll get the best estimators. We will get the estimators which are very close to the population regression function. Correct? This u, now this u will be called, I told you this u is the difference between actual and ui cap. It is the difference between actual and estimated y, or actual population regression function and sample regression function. And this will be called, it has many meanings, or I have told you, I guess, many times. It is called residuals. Fine. If we want to determine that, for example, if we want to our next job is, if we want to estimate the population regression function, like if we are dealing with we don't have population data for population, we want to estimate the sample regression function. It should be estimated in such a way that the error, not error actually, that the sample regression function should be very close to the population regression function. That is this part. Okay, this whatever I said here, I am saying it's again same. Our goal is to minimize the error. What does that mean? That means sample regression function should be as close as possible to population regression function. That's our job. So this UI I told you, it's called residuals, or earlier also I have given you different names of it. Forget it now. Don't forget it. Like, you remember that. I know you know what names I have given it, and you know it very well, right? Then what is the what is the next step? Now what we want to do is, we want to, this is ui cap equals to yi minus yi cat. This is our function. We want to minimize the sum of squares. Sum of squares, no, not sum of squares. Now we want to minimize the squares. I will not use now. Squares will come next. We want to minimize the sum of errors. No need to put it. It will work without it. We want to minimize this. Then it will be the summation, okay? Yi minus yi bar. Correct? So what is our purpose? Our purpose is that this should be the sum of this residuals should be as minimum as possible. Correct? No doubt. As minimum as possible. But if we start calculating summation of ui, the problems happen. Actually, the problems happen. If we start collecting the data and it is the estimated conditional, is the I told you the condition, it will be the mean or it will be the summation of different terms. Problem happens. What happens? Problem is this will not always give us the correct result because sometimes it will approach to zero, and that time we will not be able to find whether the error really exists or not. That is the problem. Okay? We will not be able to find. So this as minimum as possible is what? Here. As minimum is possible what? Sum of residuals, okay? Sum of residuals should be as minimum as possible. Correct? No doubt in it. Then what is the next point? The next point is like how to do this, like how to get the summation, how to get this value, like how to get this value as minimum as possible. That's our what is it called? That's our job. Like now, not job. That's a challenge, or you can say that's our goal. That's our job. Whatever it is. Our work is to minimize the error, to minimize sum of residual should be as minimum as possible, so that the population so that the sample regression function will be as close to the population regression function as possible. Right? That's because then what will happen? Then only the estimations are correct. Estimations are like then only the estimations will be best. Error free, best. Okay, it will be best with the least when the variance is least between when variance is least. It is not the term variance I'm using is difference actually, or the variance are difference. And the variance between the population regression function and the sample regression function is least. That time, our estimations are best. But the problem is, if we start calculating the population regression function, if we start calculating the sum of residuals, some error happen there. Okay, so that error will happen like this. I will plot a graph, for example. Okay, wait. See how straight line I can. That is a practice. Here. This is the graph. Okay? Then, for example, I will plot any line here. Very important. It is going to sleep or wait. Let me use it. This is our graph. Then what we have, for example, we have two things here. I'm trying to make it very neatly. It is not coming neatly. That is the thing. It's not easy to write online. See how this is. This is one. For example, 1 point from here, I will write it. Then next point I will write here. The next point will plot from here. Oh, like this, and the next one is here. So what is this? These points I will plot here. Okay, wait. This is the first point, this is the second point, this is the third point, this is the fourth point. Okay, so this line will be sample regression function, correct? And it will be derived with the help of, or it will be like how we will make it with the help of this function. Correct? Then this difference, for example, we will name as u1. Okay? This difference. Okay. Then the difference from here we will name as u2. Then difference from here to here we'll name as u3. These are estimated ones. Okay. Then the difference from here and here we'll name it as u4. Estimated. And this line, like for example, there are a lot of points on it. I will not plot any points, let it be known. So for example, if we are trying to do what we are trying to do, if we are trying to do here, if we are trying to minimize the errors, but the problem is the summation of errors here will be, it will not show us the correct result, because if we start summing up the errors, because see, for example, consider this first case, it is first, okay, first case and the fourth case, the difference is same. Second and fourth, the difference is same. Consider it. Or any points, you can plot more points in it. That's not the problem. The point here is the difference. If we start calculating the summation of ui, then it will be equal to what? It will be equal to 0. Why? Because this will be like these are the errors. This is big error here, for example. First one is big error, fourth one is big error, second and third one is small error, but these will be parallelly equal. Parallelly these will be equal. So when we sum up plus and minus, it will be 0. For example, I will give you the example. For example, the error in the first case is, for example, 20. This is plus 20, correct? In the first place. And in the second UI, it is, for example, 5. No, it is minus 5. Correct? Then in the third place, in the third UI, it is plus 5. And in the fourth UI, it is minus 20. It's like this. The first problem of only doing summation of UI, the first problem is that it will not highlight the error. It will make it like it will give us the wrong estimation. For example, if we do summation of UI now, what is the summation? 20 minus 5 plus 5 minus 20, where we have summed up the error, these 4 errors. So it will be equal to 0. Then what is the error? Is error 0? No, error is not 0 in our case. Error is not 0. What is the error? There is some error. There is some error that is very visible for us. There is some error. But simply by doing this, we will not be able to do it. Simply by summing up. And the second problem of this is it gives equal weightage. For example, it gives equal weightage. It converted this also into 0, 1 and 4. It converted it 2 and 3 also. It gave equal weightage. Otherwise, what is the case? The error in 1 and 4 case is larger, much larger than the error in 2 and 3. Okay, error in the first error residual 1 and error in the residual 4 is much larger than the error in U2 and U3. But with this method, for example, if we even calculate, for example, error in U1, for example, I will write here U1, error summation of U1 plus U1 U4, that is also equal to 0. Summation of U2 plus U3, that's also equal to 0. Then what is the it is treating them equal. Okay, you are getting me or not? This is the main problem of it. Here the theory develops. Here, this is the main problem of it. This is the point to remember. Here the main problem exists when the summation, for example, summation, how it has come. Okay, you know it very well. For example, error summation of U1 plus U4 is, what is it? 20 minus 20. It is equal to 0. So we have got 0. Okay, fine, we have got 0. Remember it. Then what is about U3 plus U4? That is minus 5 plus 5. That is also equal to 0. In both the cases, it has given 0 and 0. Here is the main problem. When it treats both the errors equally, then it will not give us the correct error and correct estimation. Okay, when it does not give the error component correctly, when it doesn't treat the error component correctly, there is the problem. Got it? There the problem exists. Okay, so how to deal with it? Because we have seen U1 equal to 20, U2 equal to what is that? U2 here minus 5 plus 5 minus 20, minus 5. U3 equal to plus 5 and 5 and plus 5 same. U4 equal to 20. The error 20 and 20, U1 and U4 is larger error. Error in U1 plus U4, okay, is much larger than the error U3 plus U2. Okay, summation, actually, I am just saying, in actual sense, error in U1 and U4 are, you can say, simply, individually also you can write. Like, no need to write the plus. Error in U1, U4 is larger, much larger than error in U3 and U2. U2 or U3, same thing. But with simply adding up, it gives errors equal to 0. Okay, when we add up, simply when we add up, the error will be equal to 0, and that is not the correct estimation. The problem happens, it gives equal weightage. So and large error. It gives equal weightage. When it gives equal weightage, what happens is equal weightage means it treats them equally. It doesn't like when we sum up the errors, we get the result the same. What does it mean? When we sum up the errors, for example, u1 plus u4, it is 0. When we sum up u3 plus u2, it is also equal to 0. That means equal weightage. What does it mean? It doesn't highlight the error correctly. It doesn't estimate the error correctly. It doesn't do that. So there exists the problem. I have told you here the problem exists here. It does not highlight the problem correctly, and after summing up the errors, it gives equal weightage to each and every one, whether it is large or small. It treats them equally, and the sum of errors will be equal to 0. Then what problem exists for us? It will not give us the correct estimation. Estimation of what? Correct estimation of errors. And when we don't get the correct estimation of errors, we will not be able to realize why the problem happens. According to this, for example, if we treat this according to this, error is 0. Error is 0 means, according to this, means sample regression function is equal to population regression function. But that is not the case actually. That's not the case. Okay. In actual sense, there is error. How to remove this problem? How to remove this problem? We will simply do one thing. Oh my God. Has again come. Add up more slide. And we'll do example tomorrow or next class. Need to do it today. I will only show this much. How to remove this problem? For example, we have error here. UI, for example, UI. How to error, for example, I will give the example of this only. UI. We have U1, U2, U3, U4. How to get rid of this error? I will show you how. If we scare the error, and get it a summation, then we will be able to get the correct error. How? For example, we have this earlier example only. Okay? U1 is equal to 20, U2 is equal to, what is it equal to? Minus 5. Minus 5, U3 is equal to plus 5, and U4 is equal to minus 20. Now, for example, I will show you how. For example, if we do the square now, if we do the square and then sum. First, we will do the square. U1 square equals 20 square equals to the 400. Correct? Then U2 square equals to 5 square equals to 25, and U3 square equals to, it is minus, it is 5 square equals to 25, because when we do minus square of minus, it will become plus 25. Okay, 2 times, 3 times it will become minus again, and U4 equals to minus 20 square, it will be also equal to 400. And then when we sum up, if we see the difference between first term and second term, for example, or if we sum up as a whole, U1, U2, U3, U4, summation of U1 plus UI, summation of UI, for example, not be written like this. Summation of UI means it is equal to 400 plus 25 plus 25 plus 400. Now how it is 4 for 8, 850. 850 is the error. Now it is showing some error. Now it has shown. Earlier, when we were doing simply here it is here because it's the sum of squares. It's the sum of squares of error terms. When we have done this square, then it highlighted the problem and we got the actual error. Correct? Then what is the next? The next thing is, if we see the difference between the larger error and smaller error, now it will show the difference. For example, if we do summation of u1 plus u2 square wala, square wala, summation of square estimator error terms, square error term or square residuals, not u1 and u2, u1 and u4, because those are equal. That will be 200 plus 200. That will be 400. Then if we do summation of u3 square wala, then plus summation of u2. What am I writing? Square u2 and u3. This is u2 square. That is equal to 50 plus 50. That is equal to no 25 plus 25. 25 plus 25. That is equal to 50. Now you can see the change. After squaring, we highlighted the problem. That highlighted, I will say in another terminology, it is magnifying the problem. It is highlighting, magnifying, making it big. What happens when we make it big? We can see it clearly. For example, you can see your mobile in the mobile screen. When when the text is small, what you will do? You enlarge it. You expand the screen, like you do the pinch, no, double pinch, expanding. You make the picture big so that the things will be clear. Same thing this is doing. It is doing the same. It is magnifying the things. So what is the actual error now? For example, difference between the difference. For example, difference is, it is, for example, I will give it u5 and u6 name, u5 and u6. u5 is u2 u3 summation. u5 is for example, it is 800 u5. Summation of u1 and u4 is u5. u4 plus u1, u2 plus u3 square, all square wala. This is u5. Then what is this? What is the difference? For example, u1 and u4 is 4 it is 4 no, 400 total 400. Nobody is seeing, even I am doing mistake. You don't really see, or I don't know what is wrong with you. It is not here. It is 400 plus 400. It's 800. Now you see the difference. How much difference it has come? It has come 800 plus 50. Earlier, it was showing it as 0, this as 0, equal weightage. Now see the difference. Difference is by 750. This much is the difference. This difference, or to capture the actual error, what we did, we squared. A summation of square. This is OLS. This is OLS. Okay, this is OLS. So OLS is the summation of, for example, it is a summation of square of residuals. SUAR square of residuals. We'll cut it. Okay. Correct. So this will be called OLS. This will be called. So that's about the why. What is OLS? OLS.
What is that word, sir? Square of? Square of last line, sir.
Repeat.
What is that?
Wait. I will write. It is the OL. It is the summation. See that it is a summation of square, summation of residual square. It is square of residuals. I have written here square of residuals, or you can write it like this. I will write it more cleanly or neatly. Summation of summation of residual squares. Summation of residual squares. Okay, that estimated one. Okay, this is all estimated. Remember, summation of residual squares will be, it will be called as OLS, ordinary least square. That's why it is ordinary least square. This square is that square only. Okay, this square belongs to that square which we do raised power 2. Least square, what does it mean? Least square, it highlights the this, it highlights the this error. And then what is the next component of it? Then what is the next component of it? Then, for example, I will write the last equation now. Now how we will write the equation? For example, we will write the equation. We'll write the equation like this: summation of ui. Earlier we have written somewhere summation of ui equals to this, or we have written it or not? No, we have not written it. Maybe I will write it now. We know ui equals to yi minus yi cap. Then summation of ui equals to summation of yi minus yi cap. Then summation of, okay, it is getting very wrong. Summation of ui square equals to summation of yi minus yi cap square. Then further expanding it, we will write it summation of yi minus, then what will write? This beta 1 cap minus beta 2 cap xi whole square. That is the residual sum of squares. Residual sum of squares. Correct? So that is OLS estimation. Now you say, what is the main property of it? The main property of the OLS is, it is one of the, it is having the property that it is sure, if we use the OLS, ordinary least square method, first thing is it will highlight the error. Second thing is, by estimating beta 1 and beta 2, by estimating parameters are beta 1 and beta 2, cap you can say, by estimating them. If we estimate beta 1 and beta 2, the error in beta 1 and beta 2 will be most minimum. They will have some their own property that is called best linear unbiased estimators, BEST. No, blue. I'll write in abbreviation. These are having the properties of best linear unbiased estimators. Okay, these beta 1 and beta 2 will be best linear unbiased. Why? Because with the help of OLS. Okay, then the further investigation is, what is beta 1 equal to, what is beta 2 equal to? Okay, what is beta 1 equal to, what is beta 2 equal to? That is equal to, for example, I will just write it, or how to calculate. Beta 1 is equal to, for example, y bar minus beta 2 cap x bar, and beta 2 is equal to summation of xy divided by summation of x square. It's tentative. Don't worry. We have to derive these things. What is beta 2, beta 1 equal to, and what is beta 2? That we have to derive thoroughly. Correct? It is not actually. It is okay. It is estimated one. Remember, every time we use it is estimated one. Correct? So that is OLS. When we minimize the errors in such a way, the first it should highlight the errors. It should not show any error. For example, if earlier here in case of this, it was showing error 0. Both the cases it was 0, or summation of total error was equal to 0. So it was not showing any error. And what does that mean? Sample regression function is equal to the population regression function, which I showed you here. Sample regression function is called population. It means it is the correct estimation, but that's not the truth. There is error, and that error is not getting highlighted. By squaring the error, we were able to highlight the error. And when we highlighted the error, we give the equal weightage to each and every value. We got to know how much error exists at each and every place. And by that is the property of OLS. And the OLS estimators, beta 1 and beta 2, are designed, or they are derived in such a way that the error, the property belong to them, is one of the best, and they will give the best estimators compared to other models. That's all about the OLS estimators. Now the next work is deriving beta 1 and beta 2.